everyone. So my name is Levin. I'm a senior researcher at Microsoft, and we're doing research on machine learning for the purpose of securing Azure. So I think most people would agree that having so many services available on the internet all the time is really a good thing. It's very convenient, but it also poses a major risk for the organizations that provide them. So back in 2016, around 3 billion Yahoo accounts were hacked in one of the biggest breaches of all time. And that same year, Uber reported that 57 million accounts containing information about drivers and passengers have been stolen and taken by hackers. So obviously, security is important. If you're thinking, all right, fine, these are isolated cases, they don't matter so much. So statistical analysis shows that there are over 130 events like this, large-scale targeted breaches against organizations in the US alone per year. And this number is growing rapidly by 27% per year. So this is a major risk. And if you're still not convinced, you could do a very simple experiment. You could just expose one of your machines to the internet, just provide unlimited access to any machine you own. You're going to see exactly how much time it takes for someone to discover this machine and attempt to log on. I can assure you it's not going to take very long. So security is a major concern. Organizations need good tools to help them fight against cybercrime. So I want to talk a little bit about the session goals here. So I'm going to present an easy-to-use framework that produces cybersecurity anomalies. I'm going to explain how a recommendation system can be used to find anomalous resource access. And I'm going to show how we evaluated this framework to actually show that it can provide value for its users. I'm going to provide some motivation and context. So Azure Sentinel is a tool that Microsoft introduced recently. It's basically a centralized cloud-native security information event management system. It's a system that allows you to get information about security information about all your cloud resources in a single place. One of the offerings in Sentinel is a pillar called Build Your Own ML. This is a component that basically what it does is it logs data from your various cloud resources, and then it allows you to bring up a Databricks cluster and author your own custom security analytics using that cluster. So you could basically write your own custom security analytics using this tool with Spark and provide security value that makes sense for your organization. So anomaly detection obviously comes up in this context. You may want to use anomaly detection within your custom-built security solutions and build your own ML. So this is where we come in here. Anomaly detection can be used for many different purposes, like fault detection and system health monitoring and other purposes. We are interested specifically in its use for finding security incidents. So it's a subset of an anomaly detection, and it has to be anomaly detection that's focused on security. So how can anomaly detection help with security? In a few ways. First of all, for investigation. So when an alert comes up and a security analyst or security investigator tries to understand what is going on, what's related to this alert, and he needs to explain and address and maybe mitigate the alert, then he begins the process of investigation. And in this process, surfacing anomalies that are related to the alert could be very helpful in the investigation process. Another reason is to prioritize the different events and to kind of better utilize your investigation time to start with the more suspicious events first, to investigate them first. Furthermore, it could also be used, anomaly detection could also be used for detection when we really trust the signal and when we see that the signal has clear security value, then we could actually use that anomaly detection signal to trigger an alert. In extreme cases, even block an event. if we're pretty sure that this event has a very, very high anomaly score and it's not expected, then we could even block the event. So it has many applications in a security context. And our goal is to equip the build your own ML pillar with an easy-to-use, and I'll explain what I mean by easy-to-use, anomalous access, something that would identify anomalous access. So what I mean by simple here is we want to be able to easily construct a data set where we can train our model using this rather simple data set. The interface of the model itself should be simple, as well as constructing the data. That means that we want to avoid writing complex code and maintaining all these complex rules, or maybe taking various data sets like org charts, RBAC tables, cloud architectures, and a lot of complex data sets and writing some complex algorithm that takes everything into account. Now, I'm not saying that such algorithms are not required. Maybe they are. But in this case, our goal is to provide something easy to use. All right? So we're trying to avoid that. So in our model, we just have these interactions of users accessing resource. It's very generic. A user can be anything that you think of. And a resource could just be something that the user uses. It could be users and machines. It could be users and storage accounts, users and containers, users and files. Anything could fit this kind of model. So it's very, very generic, and it's pretty simple to construct. And what we want the model to tell us is whether or not an access like this question mark here, whether or not it's anomalous or not, whether or not what does the model think about this access based on the access that it has seen. It doesn't know, again, anything about who these users are, what is their band, where do they belong in the organization. Nothing is known. All right? So let's try to formalize this a little bit. So we're given a user and resource pair, and we want to provide an anomaly score for that user accessing that resource. If the anomaly score is above some threshold, then we can decide what we want to do with this, whether we want to investigate it, surface it, block it, whatever. So one possible kind of simple solution that comes to mind, and I want to address it up front, is a solution that simply says, all right, if we've not seen this access before, then it's anomalous. Let's look in the last, say, past 30 days. This user has not accessed that resource. It's anomalous. The problem with this solution is it's simply not good enough. It creates a lot of false positives. Users access new resources all the time. This is not going to work. It's not going to deliver any value. So what can we do better? So fortunately, there is something we could do. We don't want to learn just from the history of a single user. We want to learn from similar users as well. And we could do the same for a resource. So maybe we could kind of look at profiles of users and profiles of resources, and then see if this access is within the profile of the user. So have similar users access similar resources, and maybe that'll give us better value. That's the intuition. So this thinking in terms of profile and other users and similar users, probably collaborative filtering comes in mind, and recommendation systems use these principles already. So looking at recommendation systems, we can say something like this. Say that here is my shopping cart in Amazon, and these are the items I usually buy, kind of standard items. There are many users buying these type of items, and suddenly I'm purchasing this item, this welding device. So by doing an analysis, one can see that users with a similar profile to mine do not generally purchase this kind of item. So any recommendation system would not give a high recommendation score to this item. So we can simply see that if I am purchasing an item with a very low recommendation score, then perhaps there is something anomalous about this purchase. So let's talk a little bit about recommendation engines and better understand how this mechanism works. So if we're looking at movie recommendations in this example, This is a pretty famous example with collaborative filtering. Well, the idea is that I'm given a matrix here with given ratings. These are ratings that the users that you see here assign to the movies. And what the algorithm wants to do is fill in all these missing question marks, and then we can simply recommend any cell that is unknown, that has not been rated, and the model predicts that it should get a high value. This is what we'd want to recommend. So how do we do that? So the way collaborative filtering works is it creates latent features for each movie and for each user. Latent in the sense that these features are not part of the input and they're not part of the output of the model. There are internal representations used by the algorithm to learn something, very similar to a hidden layer in a neural net. So we create these feature vectors. We need to just decide the rank of these feature vectors. So we're creating a matrix for that represents the movies and a matrix that represents the attributes of the users. So the actual interpretation for each attribute is not defined anywhere. You could think of it as if they're attributes of a movie, like F1 maybe represents how romantic the movie is, F2 how much of an action movie it is, but this interpretation may or may not be true. What is true is that these values are adjusted by the algorithm in such a way that the algorithm makes sure that whenever we do a dot product between these two feature vectors, we're going to get something as close as possible to the value that we know that the user assigned. So this optimization basically keeps going over all the known ratings and makes sure that when doing a dot product between the corresponding feature vectors, we're going to get something as close as possible to the known ratings. After doing that, through a process, there are a few optimizations, a few methods to do this. One of the ones implemented in Spark is called alternating least squares, where basically what it does is it freezes these feature vectors, assigns a value for them, and then tries to find the best values for the feature vectors of the movies, and then goes the other way around. Every time it freezes the other and adjusts once it adjusts the movie vectors and once it adjusts the vectors for the user. That's how it works, and it keeps iterating. That's why it's called alternating least squares. And what we're doing is to minimize the least squares of error between the dot product of the vectors and the known ratings. So once this process finishes, we have all our vector values. We already know the latent feature values. And now if we want to predict how would this user rate that movie, then all we need to do is do a dot product between the corresponding vectors. And we get that. All right, so that's how collaborative filtering works for item recommendations or movie recommendations, and how does that help us now that we're going back to anomalous resource access? So we have a few caveats here where this analogy doesn't fit perfectly well. So first of all, let's go back and examine our user resource pairs. What we have, we don't really have a rating. The users didn't rate the resources. The users just access the resource. So we have an access count. Now this access count does represent something about the probability that the user should be allowed access to the resource, because the more I'm accessing a resource, the more confidently we could say that I should be allowed access to that resource. Okay, so that could be interpreted as a kind of rating. The other problem we have here is that we don't really have any negative ratings. So no user is going to say, look, I should not be allowed access to that resource. So we can't use anything like that as kind of a negative rating, where someone would say, I don't like this item, I think it should get a bad rating. It's not, no user is going to say that about a resource. So what can we do about that? But we do have the missing access, the fact that the user did not access the resource. So we want to use that. So first thing we do is that we linearly scale all the values, because the values we have are average daily counts. We want to scale them to a range that we could work with, say in this case 5 to 10. And then what we want to do is create some random negative samples. So we want to distinct these values of 5 to 10, which we gave to resources that have been accessed, against resources that have not at all been accessed. So we're randomly sampling from the, let's call them the unseen pairs, and we're assigning them a smaller value, in this case of 1. And this is how we create a distinction between things that did take place and things that did not take place. And then we do a few additional adjustments, like adjust for user and resource bias. And finally, we want our anomaly score to be more meaningful. So not just assign it values like out of the box, but we want to normalize, use a standard normalization to mean and standard deviation for these anomaly scores. So then if I get an anomaly score like 3, I'm going to know that it's 3 standard deviations away from the mean of 0. So these values are a little bit more interpretable in that way. Okay, another issue we'd had to deal with was scalability. So in fact, in actuality, we don't really have just user and resource pairs, because each user and resource we get from a different tenant. So Sentinel contains many different tenants, in our case. It's not necessarily coming from one organization. And so we need to take into account the fact that users and resources are not shared through these different tenants. And so we want to process in parallel as much as possible the users and resource of each different tenant. So that's one challenge. But another problem is that some organizations, some tenants, are large enough to fit in memory. So we need Spark. We need Spark collaborative filtering to deal with that. So the way we deal with kind of the medium-sized organizations is that we use a package called Surprise, which runs locally on a single node and does collaborative filtering on a single node. So we can apply we can apply the Surprise package over a data frame, a Pandas data frame. So to do that, we can use Pandas user-defined functions, which is provided in the later versions of Spark. And it allows us to do a group by of a data frame according to the tenant ID column, and then apply our Pandas UDF on these groups that are created. Okay, so that's how it works. So basically what would happen here is that each worker node is going to run the Surprise package and run and train collaborative filtering for the data that's only for that single tenant. That allows us very high scalability, very high parallelism. But what do we do about those large tenants? If we do this for all the tenants, we may get a data frame, a Pandas data frame, which is too large to fit in memory, and Surprise is not going to be able to deal with that. So what we need to do is a pre-step. We need to first count the number of distinct pairs for each tenant, and then for all of the tenants that are below some threshold size, we can run this solution. And for those that are above the threshold size, we can simply apply one by one the Spark-based collaborative filtering, which can handle a much larger distinct pairs, a much larger number of distinct pairs than can a solution that's in memory. So luckily, there are not that many large customers that can't run on a single machine. So this actually works well, because we isolate maybe like a dozen or so that can't be run in parallel, and the rest we run in parallel. So this works well enough. Sorry. After the training, what we get is basically a data frame, 2 data frames, one mapping a tenant ID and a user to the user vector, and another one mapping a tenant ID and resource to the resource vector. Then all we need to do when we receive a new data set for evaluation, we need to do 2 joins against the data frame of vectors, get those 2 data frames, and do a dot product between them. So it's really quick, it's efficient, it works well, and it could also be used applied in structured streaming. So once the model is trained, it can easily be applied in structured streaming as well. Okay, another important item is how we evaluated this model. So I've kind of waved my hands and explained why everything should work well, but how do we really know that this works well? So we did 2 experiments for this. The first one, we used the synthetic data set, and in the other one, we used actual data from customers. I'm going to explain both of these experiments. So with a synthetic data set, what we did is that we created kind of a very sterile environment where we have a user, say, from the finance department, user from from HR department, and from sales. Each one accessing their own resources, all right? And there is no kind of no one is crossing the boundaries, okay? I'm also going to say that the access only covers a subset of this intra-group resources. So it's not that the finance department, every user is accessing every resource in the finance, but every user is accessing a subset of the resources, kind of to simulate normal behavior in an organization. So that was used for training. And for testing, what we did is we created new intra-group access. Within this new intra-group access, some access is access that we've seen during training, and some access we've not seen during training. But this is data that is still within department, so it should be fine. Even if the algorithm is not seeing this exact access, we expect that the algorithm will understand, based on the profile of the user and resource, that it's valid. Another data set we added here is kind of the cross-group access. This is the access that we want the algorithm to surface up and to find and to mark as anomalous, because someone is crossing the kind of the normal boundaries here. So in fact, what we found was that this algorithm was perfectly able to pick up everything that crossed group boundaries. So this is sort of a sanity test for the algorithm, and the algorithm passes the sanity test. And actually, when you look at the rank that the events received, these 100 events that we added, which crossed the boundaries, all of them were in the top 100. So that's obviously good. And the next experiment we did was to actually try to create a real attack. Okay, so we took data from an organization. This is actual data, file share, SMB serve data, where people are sharing files within their organization. And it turns out, this is kind of general known knowledge, that about 58% of the companies have over 100,000 folders open to everyone in the network. This is obviously a problem, but we used this problem to create an attack. And what we did was to enumerate, within the organization, we enumerated the different IPs of machines within the organization and tried to randomly access their SMB server and try to enumerate files and start accessing them. And whenever we're able to access a file, then it's highly probable that we're accessing a file that we should not be allowed access to. So we would like the algorithm to be able to mark all of these cases where we have been able to access files within the organization. So for the training, we used 1 month of data where we have users accessing machine. There are no known attacks within this training data set. And we took 2 days after, again, standard normal data that's flowing from the organization, plus the data of the attack that we know about, that we created. The algorithm obviously did not know which is which. It should find it on its own. So we want to see if the algorithm is able to find this red user over here that we inserted. So we tested that. We look at the entire data set. This is just the testing data set. And what we see is we have 3.8 million distinct pairs, distinct access pairs. Among them, we could see that the mean average score is very, very low. This is expected. And we see a minimum value, which shows the minimum value is like this means it's very non-anomalous, like standard, very standard, because it's below 0. And the maximum value here is pretty significant. So let's dig in deeper and understand who are getting, where is this like high standard deviation coming from? So we look at the data. We look at unseen valid access. Unseen valid access, it means that it's access that access pairs that did not occur during training, things that the algorithm was not trained on, but are valid. They're not what we inserted. They're not part of the attack. So we see that the maximum value for them is not very high. The maximum value for what we consider valid access was around 1.2. And then we look at the restricted access, the thing that we know that we created with a red user. And you can see how different the values are for here. Even the minimum value was already at 7.4. The mean was around 7.8. And the highest value that we see here is actually from the attack itself. So we see again that the algorithm creates a very, very clear margin between kind of the valid access and the access that we know for sure is invalid. So this worked very well in this example as well. So we have two supporting cases, one synthetic and one actual real data. So in summary, we set out to create a simple-to-use algorithm. So to actually show you that it's simple to use, this is the code. And it's actually been open-sourced. I really encourage you to download the code and to use it and see if it could help you. We're kind of finalizing the details of the license, so I don't want to get into that. I don't have anything to comment about that. But in terms of the code, you could see that it's basically a Spark estimator. You just create the model, give it all the parameters that you need. You then call the fit method. The fit method creates a model for you. And on the model, you could simply apply a transform to score your different triplets. The reason here that we have triplets and not tuples is because there's also a tenant ID. If that is not, if that doesn't have any meaning for you, then you could simply give all the tenants, say, a 0 or something, and it'll treat everything the same way. All right, so we introduced an access anomaly detection framework. It can be operated within the build your own ML pillar of Azure Sentinel. It will allow you to read in data from different agents which are installed on the different cloud resources. All that data can be accessed through a Databricks cluster where you could write your own custom analytics, including the use of anomaly detection to surface security meaningful events. This framework provides a simple-to-use API. It's really generic. It could be used on various data sets. And we really call the community to kind of use this algorithm, continue this line of research, maybe suggest new algorithms and additional things. This is obviously just the start. And I think there's a lot more to do here. Thank you.
All right, time for a few questions.
Questions?
Hey, thank you very much. The good talk. An interesting approach, actually. One question that I had actually was that kind of approach works really well for like a finite set, like when you have a finite set of resources. But for example, if you like wanted to potentially score, say, a purchase where you might not know well, you might not have seen that item before, so you might not have been able to even have it factorized. I guess that approach wouldn't necessarily work, or what would you advise in that kind of alternative where you can't, in the background, kind of like have the item user pair kind of thing as a recommender, but reverse recommender? Is that
so that's a good point. If I'm going to rephrase the question, you're basically asking how can we deal with users or resources that we've not seen at all during training?
Right.
Not
Correct.
just pairs that we've not seen, but new.
Yeah, like on scoring of a new purchase or new access. Yeah, correct.
Yes,
yeah,
yes.
spot on.
And that's right. That is one of the limitations of this framework. So it doesn't deal with new resources or new users. It just deals with seen users and resources. So if you have a new resource which you didn't train on, this algorithm is simply going to disregard it. So you need other models
Right.
to deal with that.
Yeah.
So this is not like a silver bullet that deals
No,
with
no,
every
no.
possible.
I'm not trying to put, and I'm not trying to
Sure.
like pinch a hole. I was just like thinking maybe you have another go-to that you'd advise.
Yeah,
for that.
there are other solutions
Right.
for that, not the same.
No, cool.
Thank you. Very nice talk. I have two questions actually. First is why did you choose alternate least squares and not something like SVD or other algorithms, NMF? The first. And the second one, why did you assign the ones in your matrix only to a random subset and not to all missing values?
Okay, so regarding the first question, alternating least squares is what's used in Spark collaborative filtering. So we simply used whatever was provided. We didn't set out to write our own algorithm for that. Surprise, I'm actually not entirely sure, but I think it also uses alternating least squares. I'm not entirely sure about that. Regarding your other question, it was, the other question was?
Why you were...
why we set ones.
Not why you set ones, but why you set ones only to a random subset, not to all missing values.
Oh, okay, yeah, just for performance reasons. So, like the negative set, the not set of what has been seen is just too large because we just have a very small subset of the matrix. We don't want to fill the entire matrix just to do the training. So, and we don't really need to fill that much information. Actually, the number we used was twice as much as what we had for the positive samples. That was kind of like a magic number that we found, but you know, it could change for different data sets.
Thank you.
Okay, here. Thank you very much for the talk. I have a question about the filtering algorithm, the collaborative filtering algorithm. As you mentioned that you already solved the scalability issues. My question is about if you could give us some numbers about the performance. I mean, how many millions of users and resources could you handle, and how many hours of how many computation do you need to build the matrix of the filtering?
Yeah. Okay, so I don't have the numbers in these slides, but I actually am trying to recall the numbers. We had, we ran this like in the largest use case we ran for this algorithm, we had about 5,000 tenants. And the biggest tenants within these 5,000 had, I'd say, hundreds of millions of distinct pairs, distinct user resource pairs. And for all this data set, it took the algorithm to run on a very powerful Databricks cluster with, I think, 32 nodes and 16 cores in each node, a lot of memory. I think around 128 gigabytes per node. It took it 1.5 hours. So it definitely works within like reasonable run times for this huge data set.